Okay. Which has at least so.
Okay.
So.
Continue.
Take big.
Let the shuffle on cabo.
Right here. Yes, that's all. Okay.
Should be better.
Now configurational stereoisomers. What it means? For discussion about configurational stereoisomers, you need in the compound at least one carbon atom, which is chiral carbon. And what means chiral carbon? This carbon has four different substituents. Now look, if we compare this, if we consider this molecule, this is one, and second one is this one, HCl, BRF. Now look, here you have only one carbon atom. Now let's cycle its substituents. In this molecule, you have two different substituents, but two atoms are the same. So this carbon is not chiral carbon. This carbon has not four different substituents, so this compound is not optically active compound, and we can't discuss in this case about its configurational isomers. Now, what about this one? Here, you have four different substituents. 1, 2, 3, 4. It means that this carbon is asymmetrical carbon or chiral carbon, and it means that this compound is optically active compound. Now, what means optically active? Optically active compounds can rotate polarized light plane to the left side or to the right side. Polarized light looks like light, like this. And in the lab we have a special equipment by which we can discuss about optical activity of some compounds. For example, if you pass through the solution of compound this polarized light, and if you look on this polarized light on the second end, so if this compound is optically active compound, this polarized light rotates on the left side or to the right side. So it means that you have optical active compound. Now, once again, we can discuss about optical activity only in case if in the compound you have at least one carbon atom, which is asymmetrical carbon or which is chiral carbon. And once again, chiral carbon is carbon which has four different substituents. In this case, you have only one carbon, it has four different substituents, so this carbon is chiral carbon and this compound is optically active compound.
Can you write the names, please?
Of this one?
Yes, this one is chiral.
Chiral. This chiral.
Four different.
chiral
carbon or asymmetrical carbon? Chiral carbon or asymmetrical carbon? Now, look, if you have this molecule, CH3, CHOH, CHOH, CH2Cl. Now let's discuss about this molecule. Have you here chiral carbon or carbon which has four different substituents?
No. No,
yes.
we have here.
Just yes.
We have
just how many? Two. Yes. This and
this. Yes.
Now let's open this structure, and you can see that these two carbons just have four different substituents. CH3. You can't discuss about this carbon as chiral carbon because of here you have three same atoms. Now what about this one? C H O H C H. Wait, sorry.
C.
Okay, I write like this, and then I open second one's substituents for showing you all the questions. Now let's discuss discuss about this carbon, first of all. Which substituent it has? 1,
2.
second, third, and this together, everything. Fourth. Are they different from each other?
Yes.
Yes. So this carbon is chiral carbon. Now let's discuss about this carbon.
Just wait.
Now let's discuss about this carbon. OH, H. For this one substitute, second substitute, third substitute, then this is together. Are they
No.
different?
Yeah.
Yes.
Yes.
So this
The
carbon,
same.
once again, is chiral carbon. So in this case, you can discuss about optical activity, and you can draw for this compound configurational isomers. Now what means configurational isomers? Configurational isomers are compounds which have same molecular formula, same order of atoms, but different arrangement of these atoms in this case. In this case. Now, how you can discuss about names of these stereoisomers. Remember, please, configurational stereoisomers we can divide into two groups: enantiomers and diastereomers. Now, what's the difference between them? Enantiomers are molecules which are mirror imaging of each other, like our two hands. My left hand in the mirror looks at my right hand. So they are enantiomers of each other. So if two molecule structures are mirror imaging of each other, so they are enantiomers of each other. Now look, enantiomers have same physical properties, same chemical properties, but they have different angle of rotation, this polarized light. But absolute value of this angle is the same. For example, if one rotates this light on the right side and the bond is 20, second one once again rotates on the left side, but the bond angle once again is 20. So they have different direction of rotation, but absolute value of this angle, of rotation angle, is the same. Now look. For example, for writing configurational isomers, in conformational isomers you use Newman's projections. Yeah? Here you use Fisher's projections, and now how you have to write Fisher's projection. For example, if you have this molecule, is this molecule optically active or not? Has this molecule chiral carbon? Yes. So we can discuss about its stereoisomers, about its configurational isomers. Because of you have 4 different substituents. So because of this carbon is chiral carbon, and because of this molecule is 3D molecule, Fisher projection, it's a representation of this molecule on the plane. Now look. You write like this, 2 lines. In this point, I mean that I have chiral carbon. After that, if I write substituents like this, H, CH, 3, OH, Cl. This is one stereoisomer, one configurational isomer, and if I write second one like this, H, Cl, CH, 3, OH. Now imagine that here in the middle you have mirror. Are they mirror imaging of each other?
Yes.
Yes. So they are enantiomers of each other. So if 2 molecules are mirror imaging of each other, so they are enantiomers. If they are not mirror imaging of each other, so they are diastereomers. Now look. If we consider molecules in which you have 2 chiral carbons, for example. Look. if you have two chiral carbons. This is one version. In this one, you mean that you have two chiral carbons. If I want to draw its enantiomer, so I have to write its mirror image like this. H, H, O, H, O, H, CH3, C, O, O, H. So these two structures are mirror images of each other, and they are enantiomers of each other. Yeah. Now, if I draw this version, what about this one? So this is once again configurational stereoisomer of these two structures. This is another molecule. But because of this one and this one and this one are not mirror images of each other, so they are diastereomers. So these two structures are enantiomers, these two structures are diastereomers. Diastereomers. So enantiomers and diastereomers. Diastereomers. Now look, what about physical properties of diastereomers? They have slightly different physical properties, and the main difference between them is that they have different angle of rotation. In case of enantiomers, you have the absolute value of rotation angle same. Yeah, but you have different direction. Here, the absolute value is different. In case of diastereomers, but all of them are three different compounds. All of them are stereoisomers each other. All of them. Why? Because of they have same order of atoms and they have same molecular formulas, but they have different structures, different arrangement of these substituents in the space. Now, for determination of absolute configuration, for determination of absolute configuration of these molecules, you have Kahn-Ingold-Prelog system. And you have some rules here. Kahn-Ingold-Prelog system. And here you have some rules. But first of all, before discussion about these rules, let's discuss about determination of priority of substituents. So, in Kahn-Prelog-Ingold systems, first rule is determination which group has higher priority, which group has lower priority. After that, you look how your priority decreases. If your priority decreases clockwise, in direction of clockwise, so you have R configuration. If this priority decreases anti-clockwise, so you have S configuration. Now let's discuss how you can determine which one has higher priority and which one has lower priority. So first of all, let's discuss about molecules where you have only one chiral carbon. Only one chiral carbon. Look, if you have this structure, C, O, H, F, Cl, H. So, your substituents are H, O, H, F, and Cl. Until that, you need periodic. And look, what's the atomic number of your first atom which is bonded to this chiral carbon? In this case, your first atom is F, Cl, H, and in this case, which one? O or H? O. You have to look at the first atom. If your first atoms are atoms of different elements, so you only need look in periodic table what is their atomic numbers. Oxygen's atomic number is 8. Is mass, atomic mass is 8. atoms, atomic number is 1. So its atomic number 1, this one's 8, fluorine is 9, and fluorine is 7. Okay. Let's continue on the next.
للبيرودك تيبل.
This periodic table.